Professor Mainardi is a retired professor of mathematical physics from University of Bologna. Since since November 2023, he has taught his course since last 40 years. Even if he's retired, he continues to carry out research activity. His field of research concerns several topics of applied mathematics, including linear viscoelasticity, diffusion and wave problems, asymptotic methods, integral transforms, special functions, fractional calculus, and non-Gaussian stochastic process. At present, his H index is greater than 70. Please visit his homepage for the full biography for the full biography of the author's paper, which is on the website or also on the abstract that we distributed. Uh, Professor Mainardi has a special request of putting all your questions in the chat box because there is a bit of hearing difficulty. And he will read out one by one. Also has his email address is shared in the chat box if there is further questions. Professor Mainardi, thank you for this talk. Please, you can start the lecture.
Of course, thank you to the organizer to allow me to give these lectures, and I hope to be clear enough. This is a contents. It's very long contents, but I will stay in time. The history of fractional calculus is well known nowadays because in any book there is the history about the lectures between Leibniz about the symbol, about the L'Hopital questions. The discussion led to a new branch of mathematical physics, which derivatives are no longer integer. But anyway, nowadays, fractional differential and integral equation have gained considerable popularity and importance during the past 3 decades. The list of applications is very huge, but in my talk, I will prefer to speak about the intermediate phenomena between diffusion and wave propagation, because it is based on the Wright function of the second kind. Anyway, when I started to write a book in 2010, then soon later other book appear. After my book, I was able to make a second edition last year, and it takes a lot of time for me to make the revised and extended edition, because the volume is twice the page. But another in a book in the same time is by my colleague Dietelm, which is very good for mathematicians. Also, from physics point of view, Tarasov. Then also my colleague Baleano, Dietelm, Scalias, and Trujillo, second edition. Also, my good friend from Russia, Uchaikin, he made a translation from his Russian books. Also, from Germany, we have another physicist who was able to publish 3 editions. Also, from Serbia, Atatovic and his group. Anyway, following an idea of the late Professor Kilbas with Gorenflo and Rogozin, I was able to publish a book on Mittag-Leffler functions, which in practice is the queen function of fractional calculus, which in any paper of fractional calculus, I presume you find always this Mittag-Leffler function. But with Rogozin, we are able to make also second edition in 2020. But anyway, the Bible of fractional calculus, it remains the book by Sanko, Kilbas, and Maricev. The history, of fractional calculus is summarized by these slides between L'Hopital and Leibniz. And also I take profit of some slides which I shared with the late Professor Massado about the great mathematicians who were able to give contributions. Euler, Liouville, Riemann. Here is another slides taken from Massado, because Massado was able to, was a great promoter of rational calculus, and you see these are up to 50. Of course, here we have other names which who disappeared after 1950. I would like to recall, always based on our collaboration with Kyriakova and Massado, a poster on fractional calculus, which summarize the main scientists who gave a contribution. And you see, at the end, we arrive at Kilbas. But of course, here we would have also other names like Gorenko himself, but in that time was in life. We have put only people living in that time. And also here, I like these slides, this poster, because it starts here from the book by my supervisor Caputo, and it finishes with my book. But this was 1969, and this was 2010. And here there are other books, but nowadays you find at least one new book every 2 months. So that is impossible to make a list of books on fractional calculus. Anyway, we used the Riemann-Liouville definition is here, which is usually adopted in the literature, but in my opinion, should be better to start with Abel, but nowadays they refer always to Riemann-Liouville. But surely the first definition of this fractional derivative is to Abel. If I recall to you that Professor Luchko has put slides about the Abel problem. In my opinion, the Abel problem of tautochrony should be the starting point to introduce fractional calculus to anybody. Here, as usual, the starting point is the fractional integral, which is here in these slides, which is practically a convolution between a power law, there is a generalization of this law, which many students do not know this law, but it's very interesting because it reduces to multiple integral to a simple convolution type integral. And in fact, now is important, it's very quite simple now to generalize this n to non-integer. Like the gamma function makes the same, the integral representation, to generalize the n factorial. So that is the same line of signs. So that here you see replacing n with alpha, and alpha is positive, or better, non-negative, we can have a fractional integral. Of course, we can make left and side, if you like. But it's important to note that the fractional integral has semigroup properties and the commutative property, which and also this law for the power law. This equation is very relevant because it can be extended also to the derivative. But in my opinion, it's better to introduce this function, which I call Gelfand-Shilov, because I found in the book by Gelfand-Shilov on generalized function. And in fact, this function has this property, and also another point is to derive the Laplace transform. I have to say that in theoretical physics, Laplace transform is not so well considered because it is left to engineers or electrical engineers. But anyway, in this respect, Laplace transform play a fundamental role, and so that it should be studied by any student. But unfortunately, in my university, in physics, practically the Laplace transform is ignored, almost ignored, in spite of the fact the book by Feller in probability theory is based on Laplace transform. Usually physicists prefer the Fourier transform, but anyway, in this case, it's better Laplace transform. And also, it's important to speak about the notion of derivative. Usually students say that the derivative is an inverse operator of the integral. Instead, it's not completely true because it's the left inverse, not the right inverse. And in fact, while we define an inverse operator, we have to be more careful, so that for integral, you can also integrate discontinuous function. Instead, when we derive integer, we need the function should be not only continuous, but derivable. So that this is a very simple example to see that if we integrated and then derivative, we don't get the function, but we get the polynomial taking into account the initial condition. This is very important because at school, this equation is not well known. So that now, on this respect, it is easier, it is natural to define the derivative of order alpha, not integer order, as the left inverse of the corresponding fractional integral, but not the right inverse, the left inverse. So that this is the correct definition, which now we call Riemann-Liouville. And it is very important to see that the derivative of a power law is taken from the same rule of the integral, replacing alpha with minus alpha. But of course, this needs a care because the integral in the Riemann-Liouville is become singular because it's not regular in the origin. And also another fact which is very relevant, as the derivative of a constant is no longer a constant, so that the derivative of 1 is this one. Because this is the intriguing point which as considered, it should be considered the main point of difference between fractional calculus and ordinary calculus. But there is a trick to get the derivative of a constant to be 0. It is sufficient to reverse the order. But the order, we put a star, and nowadays this is called Caputo derivative, but of course it was used also by other people before Caputo. And we say the relation between these two definitions is this one. But this definition is more restrictive because you need the derivative of integer order in here. But in this case, you see if you like to compare the fractional derivative of two functions, they are equal in the for the alpha unless a polynomial of integer order. Instead, if you consider this new derivative, new Caputo derivative, is similar to the same rule of the ordinary derivative. So the difference is a polynomial of degree m, where m is the integer containing alpha. So that we have also a difference between. And for the Laplace transform, we have this. We decide to call this the Caputo derivative. And here in the next slides, I have to try to explain the name of Caputo. And in fact, starting from the history, we have to say that this form, according to Butzer and Vespel in the book edited by Eifer, we can see that Liouville used this, but did not recognize this notion, because other people prefer to call Liouville derivative, but Liouville did not apply this rule, only he did not consider. And also in the book by Courant, also, in spite of the fact Courant was an eminent mathematician, he did not recognize the difference between this order of differentiation. Strange, but true. So that it means that also eminent mathematicians are not infallible. Then Caputo, Caputo, first of all, has 2 degrees. One in mathematician, was a physicist, but it is more relevant as a geophysicist, because he published more in geophysics, and my PhD thesis was in the application of his derivative in visco-elasticity in geophysics. Gorenflo, here is a picture between me and, but it was taken more than 20 years ago, when Gorenflo was in life, and he was just in Bologna. This is Caputo, this is Gorenflo. And after my first PhD, I did not work with Caputo, but in 94, I met Gorenflo, and both of them fall in love on the Mittag-Leffler function, so that we decided to collaborate in fractional calculus, because fractional calculus gives always to Mittag-Leffler function. In my website, I have a point in the folder just to remember the document about Gorenflo, which here. And here you can see many documents about the life of the late Professor Gorenflo. But if you like to consider all of R, and not only the positive of R, we need to use the Fourier transform, because the Fourier transform is a bilateral transform. And also it is important to define this operator, to define a symbol of course, I don't speak about the correct the precise theory, because you need books to explain these operators, but for us, for Gorenflo and myself, it was sufficient to have this rule, which we apply also in the Liouville integral, which Liouville used all of R. So that's starting from -infinity to +infinity. And in this case, we can prefer to call this Liouville derivative and but my talk is essentially all the Riemann-Liouville. But why you make this? Because as the time usually is in R plus, but the space, usually we prefer to speak about the causal phenomena, the phenomena starting at t equals 0. But for X, for the spatial, we prefer to have a infinite domain. So that we need to use the Liouville derivative and the related operators symbol, which are here. And these operator, you see, are related to only for alpha between 0 and 2. We can explain better later. Of course, this was introduced by Riesz in his in a paper in 1950. So that you see this derivative has a shorter history. And essentially was due to Marcel Riesz, which was the brother of his brother, which is more famous in quantum mechanics. But Riesz was Marcel Riesz was more relevant in mathematics. And the friends of Marcel Riesz, the great mathematician and probabilistic Feller, was able to generalize this derivative, generalizing this symbol, the symbol of Riesz, you see here, which is the logarithmic of the characteristic function of the Liouville stable probability distribution. So here you can see a relation between the fractional calculus in the Riesz-Feller framework with Liouville stable probability distribution. Liouville stable distribution nowadays are very common, but as usual, when Liouville introduced them, they remain forgotten because the variance of the Liouville stable distribution are infinite, but they contain the Gaussian. But the Gaussian is the only one stable distribution which is as a variance limited. And here I like with also with my former student Pagnini to put alpha theta in this diamond, which I copied from a paper by the Japanese Takayuso. Here we alpha 0 and 2, and theta equals 0. We have the symmetric distribution, or better, the probability density function. And for alpha equal 2 and theta equals 0, we have the Gaussian. So that the Gaussian are here, and here are the other one. Here, so that it seems to me is the best way to represent the stable distribution. But of course, is not the only one method view to see the stable distribution. But in my opinion, this is the best one to simplify the matter. And also to recognize why the fractional derivative is related to the ordinary derivative is enough to recognize this relation. You see, kappa square is a symbol of the second derivative, yes, minus kappa square, so that here you see, to make content as a mathematician, we have a power law of the positive definition operator, because this is a positive definition, and so that this is the best way to convince a mathematician to use this fractional derivative in the Riesz sense. So that Zavlansky use a notation. You know, the notation is very important because the notation by was the starting point of the question of starting the question, the method, the fractional calculus, and the notation of Leibniz. In fact, for Leibniz, it was natural to replace n with a number, a rational number. Instead, Newton used point, cioè a dot, so that nobody can think what means half a dot. Instead, to explain, to derive from n and what is one rational number, and this is also the origin of this name, fractional, but the order, of course, is real. But Zavlansky, which is a fundamental paper with Saichev, unfortunately, both of them are dead. They write the derivative of Riemann-Liouville in this notation, which, of course, is only notation, of course. And then, in the book by Sanko, Kilbes, and Marichev, you can find this operator, which can be used Riesz potential is called more than. Another which I don't speak is the for numerical. Another point to introduce the fractional derivative is starting from the this definition, but which is a generalization of the ordinary derivative in a numerical sense. A main application of fractional derivative and integral is the Abel equation. Here I refer to generalized Abel equation, which was introduced by Abel in 1826, where the first paper was when alpha was 1/2. But the mechanical problem of the tau tocron here is not described, but in my opinion is the best way to convince people of the utility of the fractional calculus, because is the basing of the cycloidal pendulus, which period does not depend on the amplitude. And in my opinion, this is the best way to introduce fractional calculus. Anyway, Abel equation is very relevant not only in this problem, but as I learned from my colleague Gorenflo, is very useful in many fields. And in fact, Gorenflo has written a book about the application of Abel. For example, we have in seismology, here probably I forgot to say equiseismology is used, and also in the solar planetary atmosphere. So anyway, it's very important to say that the Abel equation is so relevant in physical problems, so that they justify the adoption of fractional calculus. Because some people is a little bit does not like to use this, because they think to find a geometrical meaning, but it's like to understand, to ask the meaning of a fractional the gamma function is the same. If people is convinced to use the gamma function, so that should be convinced to use the Abel equation. The same, because the Abel equation is the most simple physical example of fractional derivative and integral. And in fact, this can be written as a Riemann-Liouville integral, which is solved with a fractional derivative. And in the Laplace transform, of course, the Laplace transform was not known in the Abel time, but if you use Laplace transform, this is much easier to find the solution without using the fractional integral. But because with the Laplace transform is much easier to introduce. But anyway, from mathematical point of view, we can have some different solution which depends on the relations here, you see, according to consider this derivative. You see, you can have this or this. In this way, we have a different solution. One is expressed in terms of the Riemann-Liouville fractional derivative, and here in terms of the Caputo derivative. But Abel integral equation is has also second kind when we have a function in the right side, so that this can be also solved in formal way with the fractional integral, and in this way we can use the Gelfand-Silov function always formally. Of course, I have to remember I am a physicist, so that I don't put the regularity condition. As we told with Gorain flow, we leave to pure mathematician to find the correct condition which justifies this passage. But in this way, now we found the Mittag-Leffler function. What is the Mittag-Leffler function? It's the exponential where instead of the factorial, we have the gamma function. So that when Mittag-Leffler introduced this was only for mathematical interest to have a entire function. But from physical point of view, it's quite interesting to have a Mittag-Leffler function because it plays a role to generalize the exponential. But where the negative argument? Where is important the exponential? In the relaxation equation. The relaxation equation is the most simple equation studied in physics because is linear and with constant coefficients, and the solution is a pure exponential. And what happens when the first derivative is a fractional derivative? Here we can have several choices. We can use the Caputo derivative, for example, which requires the initial condition as in the ordinary case. But if people like to use the Riemann-Liouville, we have to change the initial condition. If you like to have an equation similar to this, we like to use the initial condition as in physical sense, which is more reliable. Yes, now we can put the Riemann-Liouville derivative in the right side, and you get the equivalence between these two. And this can be solved with the Laplace transform. And Laplace transform is a simple exercise for students who are acquainted with Laplace transform, because Laplace transform reduce a differential problem in an algebraic problem, and algebraic is studied also in secondary school. This is, but here you can see here what is the Laplace transform of the Mittag-Leffler function, which can be derived also integrating by series, and you get this. Of course, the best book to study Mittag-Leffler, I presume, is a book by Podlubny, because Gorenflo and Podlubny and myself were able to outline the notion by Caputo and the notion related to the Mittag-Leffler function, so that I am honored to share with Gorenflo and Podlubny this approach of fractional calculus based on Mittag-Leffler function and Caputo derivative. And in fact, you see, in the case of A and C, we get the same solution. Instead, in the other case, we get this. But this, which function, you can understand, you can by simple exercise is as the first derivative of the Mittag-Leffler function. I have to say that it's not so common to recognize this because any people prefer to use the derivative into variable, into exponent, but this is better because we have the same function as the derivative. So that the plot of this function, which for me a function exists which is plottable, is this one. And what is this? Of course, the Mittag-Leffler function was also applied by eminent mathematician after Mittag-Leffler, but the most application you find in fractional calculus problems. And you see, with respect to the exponential, we have a power law decay, so that very low decay, but very fast in the beginning. So that is strange, this fact. It is very fast decay and then slow decay. This can be also considered a stretched exponential, if you like. The best things to see is also in logarithmic scale, because in logarithmic scale, the power law decay is a straight line. Instead, the exponential is this one. And you see that it's singular when alpha is close to 1. This singular limit, it was considered also by eminent mathematician like the late Professor many mathematicians consider this singular effect. Is singular because a power law cannot go to exponential in a continuous way. I would like to point out the paper, a recent paper published by Richard Paris, which unfortunately died quite recently. I was honored to have some paper with him, but it was interrupted by his departure. So that the derivative is singular in the origin, of course. And here you can see the decay for t tending to infinity. The problem, because I introduced the derivative in time, I prefer to use the Caputo derivative, and I would like to generalize the diffusion equation, because after the relaxation equation, what is the most simple differential equation studied by students is the diffusion equation and wave equation. So that here we have always first derivative or second derivative. And here we have second derivative. So that the best way, the fractional way to generalize this is to replace the second derivative in space by the Riemann-Liouville, but the Riesz-Feller derivative. And here we can see here, and here we studied, and these generalization are very important to convince students that to generalize not only for mathematical point of view, but from physical point of view, because nowadays there are several applications which generalize diffusion and wave propagation. In order to be on time, I prefer to skip this because are contained in the paper with Luxco and Pagnini, published in 2001 in Fractional Calculus and Applied Analysis. But anyway, the problem is always, we return always to the Mittag-Leffler function, because here we have to invert in Fourier and Laplace, which is related when I I invert Laplace, we get the Mittag-Leffler function. Then we have to invert this in the Fourier transform, and we get what? Another function, which in the standard case is the Gaussian. Of course, this was natural to find the Gaussian. But when is not alpha is different from 2 and beta different from 1, we have or equal 1, but alpha different from 2, we have to work, and we get the stable distribution. Nowadays, stable distribution, there are books on stable distribution, so that is no longer a novelty. But when I started this, I was attracted because not only the application in visco-elasticity, where we have a memory effect, but we can justify the Lévy stable distribution, which play a fundamental topic in anomalous diffusion and also in finance, because in finance we cannot have only the Brownian motion, because Brownian motion does not allow steps, but only continuous line. So that it was very important, my collaboration also in so-called econophysics, so that it means finance from a physical point of view. And here we get, of course, the generalization of the Gaussian, the stable distribution, which can be the topic of another talk. But I would like to say what is this formula. This formula is express the resolution of the standard problem of the diffusion wave equation in terms of the two functions. One L, which I refer to alpha to the Lévy stable distribution, which I have a very known expression in series. And here is a function which I call M, because I introduced as an exercise when I taught mathematical methods in physics. Instead to say to my student, I make a paper, but it was an exercise of fractional of the third year of physics, no more, no less. But the only thing is to generalize the expression in Laplace transform when the exponent was not 1/2 but beta or nu. This was my, because, and then I introduce this function which I would introduce then. Okay, the problem is it's still a stable probability density function. But we found with Lucio and Pagnini, we found this condition, which is here. Here are the conditions where we can have a probability distribution. And this is also used by our colleague physicists like Messler, Cheskin, or probabilistic like Begin, Scalas, that use this approach. So that I have to explain what is this M function. Yes, this function is the so-called Wright function. Wright function is, I learned about this in the book, in the handbook, as I learned a Mittag-Leffler function, because you see, if you look in the ordinary handbook of function, you don't find a Mittag-Leffler and Wright function. Where I was able to find in English, of course, because in the Russian literature was different, but I don't know the Russian, unfortunately. And because of the Cold War, we are not able to read Russian. But nowadays, almost many books in Russian and papers are translated in English. But nowadays, not when I was a student in '69. Okay. Now, just to say what is my origin. The origin is the handbook book by Batman project. In the Batman project, in the volume 3, in the chapter 18, related to miscellaneous function, miscellaneous, so that not miscellaneous, what means, yeah, you find Mittag-Leffler and Wright function. But unfortunately, in the Batman project, lambda here is considered positive. I can show you the page, so that for me, it was an exercise to improve the result contains the Batman project. But then I learned that Wright wrote this later in a paper in 1940. Okay, of course, so that's my property. But anyway, there is a difference between lambda greater than 0 or a lambda less than 0. Of course, here I like to define the right, distinguish the right function in two kinds, because they play a different role when you make the Laplace transform. Also, this is not well known in the literature, because usually they speak about this formula. But this formula is valid only if lambda is greater than 0. Or, yes, when lambda is negative, and I call minus nu, okay, is different. You see the difference between this formula, which it was also shared by Luczko, which was a pure mathematician, so that I'm sure that my result was correct, in spite of the fact that many people use only this. Of course, there is a relation, a continuity. When lambda equals 0, of course, we can get the same solution. What is the I call this second kind function, and this I call first kind function. Right function, second kind. Because this is a very important, and which Paris and but also in the Wong book, in the Wong papers, they distinguish the two kind of right function. But I prefer to use I prefer to point out the second kind, because in the second kind are the solution related to the solution of the fractional diffusion wave equation. And what do you find? You find that the asymptotic expansion is a stretched exponential, with stretched here, and a power law, so is a combination. And when nu equal 1/2, we get just the Gaussian, which is no longer an asymptotic expression. Of course, if you like to look in the, you can relate the right function of the first kind also with the Bessel function, which, but anyway, this is a general relation, which can see also in the book by Batman project. In my opinion, the Batman project remains the best book of functions. Well, when I introduced, as I told you, the fractional diffusion wave equation in '93, yes, as an exercise, I found that the solution of the standard boundary condition are this function for the initial condition, and this for the other problem. These are introduces, and I have to say, whatever the symbol, instead to use WW, I prefer to use a symbol, and I used my initial, because in my opinion, I was original, because when I learned this, no, my source was only the button project, where again, I repeat, lambda was positive and not negative. Probably for image print, of course, because anyway, and the motivation was based on the inverse of a certain Laplace transform to obtain the fundamental solution. And these functions are also expressed in series, which I can show, which are entire. This was my exercise to prove to entire. But of course, also Wright before me proved the same. But I repeat, it was independent of Wright. Of course, the integral representation is this one here, and you find also in my books on the Mittag-Leffler function, we devote a chapter on the Wright function because they are related to Mittag-Leffler function, and also in my book on Visco-elasticity overall in the appendix F. But I would like to show you that when nu is 1/2, you see, you get the Gaussian. When alpha is 1/3, we have the Arran function. And when Aniga, my friend Aniga, was able to find a relation with Arran function, and then I asked to Paris, which was expert of function, and also my former student Consiglio, to see if it's possible to generalize, to find the generalization of the M function when the order is fractional. And you arrived, yes, were able to find something. I refer to the paper by Paris and Consiglio. Yes, so that I come back again to time flux diffusion wave equation, because when the time fraction diffusion wave equation is, I say time because the derivative, because the order not rational, not integer is in the time, so that we generalize the fraction, the diffusion wave equation only in time. Okay, and then working from a mathematical point of view, these are the two problems. The Cauchy problem is an Alling problem. This the Cauchy problem is usually considered by mathematician. This is usually used by physicists and so overall in seismology. But anyway, there are two typical problems, more simple problems to find a solution. Of course, when alpha between 1 and 2, we need another condition, because you see, in the Caputo sense, the fractional derivative is a convolution with the integer derivative, order 1, so the order is less than 1, and over 2 if the order is between 1 and 2. So that you need another condition. For continuity, we put gx equals 0. And also another things which we learn from my papers is this reciprocity relation, which is a generalization of another relation we find in any book on diffusion equation. And I told you the fundamental solution of the Cauchy problem is related to M function, and the fundamental solution of the Alling problem is related to the F function. So that it is relevant to consider these two functions, which I called auxiliary functions. And what is the plot? Because, as I told you, in order to understand function, you need the plot. Just to see, allora, for alpha equals 0 and 1/2, you see the passage between the exponential to the Gaussian. Then, when alpha between 1 and 2, in our case era beta, or nu between 0 and 1/2, depends on what I call. Here I use nu. Nu is between 0 and 1, but the order is twice. And what you get? The fundamental solution of the wave equation is, as you know, is the two delta function. So that we see that this function from the Gaussian, which is only one we see two, and you see like an function, M letter. But at the end, this restrict, and then you get C2 delta function. For n equal enough, we find back the diffusion equation and becomes a Gaussian. When nu tending to 1, we have 2 delta Dirichlet delta function. But now it is important to see, to convince people of the utility of this function, because nowadays more mathematicians prefer to use more general function, because the Fox function. But as a physicist, I prefer to use only one parameters, and in this case nu, and to use this function, so that I would like to see what happens in animation. So that I asked to my former student Consiglio to make this animation. This animation is here. You see from with the order from the exponential, you see when u tending to 1/2, we get the Gaussian. It is only a question of time, but so that I am grateful to Armando Consiglio to make this animation. Then this is a Gaussian. Then we stop a little bit, and now we see this. Of course, I cannot consider the case n equal 1 because the delta function is not a function, cioè is infinite. Okay. Okay, just to finish, just to say the priority, because I always, because I made simple things, I found always, now terrible. I have to go back to my Zoom. Now is a point. Ecco. I hope so. No, stop share. I have another slide, but niente.
We can see your share. We can see your slides.
What is the last slide? I don't see.
The last slide is one where it
yes,
has the
yes,
YouTube
is
link.
one, but I don't see big. I don't see the big. Anyway.
Probably you should close your animation, YouTube animation.
Yes, I see here.
Then you will see slides.
I try again. But you know, you have a... But anyway, it's just to say that my plot is also contained in the book. Let me see if I am able to. No, but anyway, I don't. Anyway, the last you can show the last slide, which I'm not able to show. I don't know.
Yeah,
why.
sure. I'll share.
Show for me.
Yes.
Eccolo qua. Again.
This one?
No, the last one. Again. Yes, one. Ecco, it should be noted that the German mathematician Pruss, in his book, present a plot which is reporting the M Wright function, and a plot which was based on the Fujita paper. I have to recognize that when I make in the same year my condition, I did not know this book, so that probably Pruss probably thinks I copied to him, but it's not true, because I was acquainted by his book later, and also his book is based on the Fujita paper. Instead, my conditions are different. Was not the inverse of the Fourier transform of Mittag-Leffler function, but was based on the Laplace transform, so that surely is independent. But you know, because I made simple things which are shared by other people, for example, I speak about fractional visco-elasticity. I had a problem with the Russian, like because they have the paper by another Russian, which anyway, it was independent. It is very easy. When you make simple things, it's very natural that someone before you or the same time of you has made the same. This is just to say that I'm able to publish simple things which can be shared also by students, not only by eminent mathematicians. Thank you very much.
Thank you, Professor, for the nice lecture. Would you be able to take the questions online, or
Yes. No, I prefer
or on
chat.
chat?
I prefer
Okay,
chat.
I see. I request the audience to kindly write your questions in the chat.
Allora, vabbè. Of course, we have learned from, I reply to the question of Luchko. Luchko, of course, was able to generalize the inverse of Riemann-Liouville integral in several ways. And you have learned from the lectures by Luchko. And I have to say that I know Luchko when he was postdoc student from Gorenflo 30 years, so that he was able to learn more than myself from Gorenflo, and that he was able to generalize the fractional derivative with Sonin integral. And my reply is to look at the lectures by Luchko, because it is out of my competences, grasp, if you like, because I remain to my slides. Then I don't see other question.
So thank you very much, Francesco, for your very nice lecture. Of course, you contributed a lot to the basics of fractional calculus that are, in my opinion, very, very important.
Yes, I would like to say that if people would like to contact me, I'm at fracalmo@gmail.com. The email I put in the first slides, you know. I am glad to send the papers, also the slides, and also to reply to any question if I am able to reply. Of course, the question of Luchko, I refer to his paper, to his lectures, because my reply is I know the paper by Luchko, but only he is able to reply to question related to other fractional derivative. My opinion, my knowledge, it remains to the classical Caputo derivative, which I'm honored to have introduced with Gorenflo and Podluni this name, because in other case, probably Caputo remain unknown to mathematicians, because he published in Geophysical Journal. And also I am glad to have known very good mathematician like Paris, who has shared with me some paper with, and also on special functions. And also I am honored to have good students like Pagnini, Consiglio. I would like to say that my return to fractional calculus was in '93 with the thesis of my student Ombretta Pinassa. This was an occasion for me to go back to fractional calculus because before, when I started in late 60 to speak about fractional calculus, people laugh. No, we have to remember that fractional calculus remain, is common just when fractals became sonfacial. Our fractal people use the derivative of non-integer order, so that it is natural to come back to fractional calculus, which is a misnomer, of course, and remember that eminent mathematicians like Abel, Riemann-Liouville, and so on have already published on this, so that there is no laughing to say. Probably nowadays there are too many applications because it is natural to generalize the only integer any differential equation in from integer order to non-integer order. But the problem is the application. It seems to me anomalous diffusion and passage from diffusion to wave is find many application. You can look at books by Tarasov, for example. Okay.
Okay. Are there any more questions or comments before we close? Any final remarks from anyone? Okay, so we close the talk here. Thank you, Professor Mainardi, for the insights and for the nice lecture. It was a pleasure learning from you today.
I ask pardon if I make confusion, but you know, one thing is my late age, but the other thing is my style. My style is confusing. I'm sorry. I prefer to write than to speak.
Anyway,
Thank you very much for your
thank you.
attention.
Thank you, Professor.